All right, good afternoon. How's everybody doing?
Good, are you?
I'm doing well, thanks. Alive is good. It's definitely where you want to be. All right, any questions from last time? We were starting to develop set theory and we ended up with the notion of equality of sets. And we talked about the empty set and sets of sets, and I promised some weird stuff at the end of the week.
So, I have a question.
Okay.
I'm not sure if it involves what we went over last, but I was looking through the homework. How do you multiply two sets together? How does that work? What does that look like? I tried to find it in the text and I couldn't.
Okay, we can talk about that now. So there's something called the Cartesian product of sets, and it works like this. It's basically taking combinations of pairs of things. So let's suppose I have a set A which contains the numbers 1, 2, and 3, and I have a set B which contains the letters X, Y, and Z. So there's a way to combine these which is called the Cartesian product. And the Cartesian product is a set, but each thing in the set is what we call an ordered pair, which is a pair of things inside parentheses separated by a comma. And the Cartesian product is all ordered pairs where the first thing in the pair comes from A and the second thing comes from B. So for example, it would be a set containing the following ordered pairs: 1 comma x, 1 comma y, 1 comma z, 2 comma x, 2 comma y, 2 comma z, and the same with the threes. So the Cartesian product of A and B is a set containing 9 things. Each of those 9 things is an ordered pair of 2 things, where the first thing comes from A and the second thing comes from B. And in one of our notations, we could say it's the set of all, I don't know, let's say little a comma little b, such that A is an element of the set big A, and B is an element of the set big B. So that would be a definition of A cross B, or the Cartesian product of A and B. And we'll come back to that and we'll look at what that means in more interesting cases than 1, 2, 3 and X, Y, Z. And it's actually got a good mathematical meaning for different kinds of sets. Does that help for the homework?
Yeah, thank you so much.
Okay, cool. Welcome. All right. How many people have been able to log into the Linux server successfully? Let me see a show of hands. All right, that looks like about half the class and half the class not. And it may be people aren't responding yet, or you haven't succeeded. Oh, even figured out how to do it without the password. Cool. So if you hop onto Canvas, and hop over to the 215 page. this how-to quick start guide will tell you how to get into the server. So the server itself is linux.engrcs.com. That's that. Your username is first initial followed by last name with no period, no punctuation, no extra numbers, nothing. Okay, just first initial last name, unless your last name has a hyphen. And then your password is your 9-digit CTC link number followed by an underscore. All right, so make sure that you've been able to log in, so that when we want to start using the server in class, we can do that. All right, so let's continue developing some of this set theory stuff. So Venn diagrams, people encounter this somewhere in school, most likely. But let's do a quick run through on Venn diagrams. A Venn diagram is a way to visually display things related to sets. So for example, we might have a set of cookies. And so this has chocolate chip cookies, sugar cookies, snickerdoodles, thumbprints, all these different things. And this might be the set of foods with chocolate in them. So candy bars and chocolate ice cream and things like that. And these might be elements of a much bigger set, which we can call the universe, which is the set of all food. So here's the set of all food. That's the set of all things that we can use to build our sets. Here's a set containing all cookies. Here's a set containing all foods with chocolate. And there's some overlap, right? So chocolate chip cookies belongs to this set and also belongs to that set. And if we want to make a meal and our meal is going to consist of cookies and foods with chocolate, we can look at everything that is in either or both of these sets. So we can do what's called taking the union of them. And if we want to make a meal that has lots of food in it but does not have any cookies or anything with chocolate, right, we could look at everything that is outside of those two sets. That's something called the complement. And would be everything other than whatever is in those two sets. Now, we can't do proofs with Venn diagrams. Okay, we can't prove something about set operations using Venn diagrams, but we can use them to help ourselves understand what's going on. A big part of this course is about proofs. Okay, we're gonna spend a lot of time working on proofs, studying proofs, getting better at doing proofs. But a proof is really nothing more than a formal presentation of something that you already know is true. And a lot of times we know that something is true, or we think that something is true before we know why. We have a feeling, right? If I take A and I put it together with set B, I should get the same thing as if I take set B and I add set A to it, right? I feel like that's true. But can I prove it? Well, you try to figure out why you feel it's true. You try to find some counterexamples and see why you can't find a counterexample, right? So Venn diagrams can help with sort of exploring that intuition. But then ultimately we want to come up with some kind of formal, rigorous proof that we can present to somebody who doesn't share that intuition, who maybe doesn't even share that belief, who doesn't think that this thing is true, and we can present a logical argument that once they get to the bottom, they're forced to say, ah, yes, okay, I agree, the thing you stated is in fact true. And that doesn't always happen. There's a branch of mathematics called algebraic geometry, and there was a school of mathematicians in the beginning of the 1900s who took huge leaps forward in this field, but a lot of their work was based on gut feeling. Things that they knew was obviously true, and they built on top of that. And sometime later, a lot of the results they came up with started to fall apart. because there were things they thought were true that turned out not to be, and they hadn't gone through the rigorous step-by-step process of proving these things. So rigor is important, and even if there's something that we know absolutely is true, like if I take two even numbers and I add them together, the sum is going to be even, right? 10 and 8 is 18, 12 and 2 is 14, right? An even plus an even is always an even. But can we prove that? Okay, so we'll be getting into that in a few weeks. So Venn diagrams help us understand what's going on, but they don't take the place of a proof. Just like saying 12 plus 2 is 14 doesn't prove that any two even numbers added together gives us an even. But it gives us a way to explore that intuition, right? All right, so we talked about equality of sets. Let's talk about something called subsets. So subsets is a version of equality. So here's a definition. A set A is a subset of a set B. And we write this with the following symbol. So A with this sideways U with a line underneath it, that means A is a subset of B. If every element in A is also an element of B. So A is a subset of B if every element in A is also an element in B. So for example, A equals 1, 3, 5, 7, and so on equals positive odd numbers. And do you remember what the set Z is with the funny double slash on the diagonal?
That's the set of all integers, right?
That's the set of all integers, right? So we can make the following statement. A is a subset of Z. What that statement means is that every element in A, every positive odd number, is an element of Z. It's an integer. Right? And we know that's true. When we talk about positive odd numbers, we understand we're talking about integers, right? So everything in here is an element of Z. On the other hand, we can have the set of all prime numbers, which is the numbers 2, 3, 5, 7, 11, 13, 17, 19, and so on. So numbers that aren't divisible by anything other than themselves and 1. And A is not a subset of P. Why? Because A includes the number 1, which is not in P. A includes the number 9, which is not in P, and so on. And we also find that P is not a subset of A. If this 2 wasn't in here, P would be a subset of A. Because every number in here is an odd positive number, and so it would be contained in A. But because P also includes this 2, P is not a subset of A. All right, so someone asked the question in chat, which is where I was about to go. something called proper subsets. So here's a claim. For any set A, I claim that A is a subset of itself. Now what do you think? Is that true? Give me a yeah. Give me a thumbs up or a thumbs down. Or a chat message. Thumbs up, yeah. Cool. Okay, so we have consensus here. A is a subset of A. That is in fact true. And it almost comes directly from the definition, right? A is a subset of B if every element in A is also an element of B. Well, if we say A is a subset of A, all we have to prove is that any element of A is also an element of A. Well, that's kind of gotta be true, right? But we could make this a little bit of a formal proof. Pick any element E contained in A, then E is contained in A, right? Therefore, A is a subset of A. All right? It's almost too simple to actually do a formal proof, but I've just applied the definition. I picked an element of this set, and I showed that it's an element of that set. And that is enough to conclude that A is a subset of A. And we're not going to talk about if A is a set of all things not in A yet. But that's a good comment in chat, and we are going to talk about that. But that's Russell's paradox. All right, so A is a subset of itself. That's always true. Another thing I can say is the empty set is always a subset of any set A. And that one's a little harder to get warm and fuzzy about, right? Because the claim is that every element in here must also be contained in there. Well, there are no elements in here, so kind of by default, right, any element that's in here is also in here. It's a little wiggly, and we'll play around with that more when we get to logic. But it turns out every set is a subset of itself, and the empty set is a subset of every set. Which means, of course, that the empty set is a subset of the empty set for both of these reasons. So every set has two subsets, but those aren't really terribly interesting subsets. So we have a special notion we can use, which is this without the bar underneath. And sometimes you see it written like this, although this is harder to typeset. But something that indicates that we're writing A subset of B, but we don't have that bar underneath. Okay, this is a definition which means A is a subset of B in the common sense, and A is not equal to B. So in common speak, we would say A is an interesting subset of B, right? Because B itself is a subset of B. That's not a very interesting subset. It's just the set itself. So this is saying A is a subset of B. This is saying A is a subset of B, but A is not all of B. It's somehow at least a little smaller. All right, so that's the notion of subsets, and this is what we can call a proper subset. All right, well now we can make a more interesting theorem about sets. So we can use subsets to make some statement about equality of sets. Remember we talked about two sets being equal, meaning they have the same stuff inside. Something is an element of one set if and only if it's an element of the other. Well, so here's a theorem. And you know, if we do a very formal mathematical proof, I can't just say something about A and B unless I tell you what A and B are. So I'd have to say, for any two sets A and B, comma, and then I could write out the rest of this. This is not a math class per se, okay, and it's not a logic course per se, so we'll get a little relaxed with our notation sometimes. We've been talking about sets A and B for about 10 minutes now, so I'm just going to say, you know, A equals B, and we're going to understand that these are sets we're talking about, okay? But I want you to know I'm being a little sloppy here. So A equals B if and only if A is a subset of B and B is a subset of A. So two sets are equal if and only if they are subsets of each other. And we can prove this. Well, if and only if means we need to prove two things. We have to prove that A equals B if this is true, and that A equals B only if this is true. Okay, so before I do a proof, let me write out both of these things. If A equals B, then A is a subset of B and B is a subset of A. And that's one thing this statement says. The other thing it says is if A is a subset of B and B is a subset of A, then A equals B. So we really need to prove both of those things. And I'm not going to go through this in complete rigorous detail, but I want to just give you an idea that we basically just keep going back to the definitions. So let's prove one. We're given that A equals B, right? If then, so we're told, suppose that A equals B, we should be able to show that each is a subset of the other. Okay, given that A equals B, well, come back to our definition. We can write A as a subset of B if every element in A is also an element of B. Well, that's the definition of equality, right? So pick any element contained in A, then that element is also contained in B because of the definition of this equal sign. Well, we just stated that for any element in A, it's also an element in B. That's our definition of A being a subset. So we can say, therefore, A is a subset of B. And I can do the same thing but flip it around. Pick any element F contained in B, then F is contained in A. Therefore, and my three dots here is an abbreviation for the word therefore. And we say therefore a lot when we're doing proofs. It sounds very fancy. Therefore, so we say it so often we have an abbreviation for it, three dots in a triangle. Therefore, B is a subset of A. So given A equals B, we've proven A is a subset of B and B is a subset of A. Therefore, statement 1 is true. And we do exactly the same thing to prove statement 2. We would say, suppose A is a subset of B and B is a subset of A. Well, now pick an element of A. Since it's a subset of B, it's also an element of B. and pick any element in B, and since that's a subset of A, it's also an element of A. And we've just shown that any element of A is also in B, and any element of B is also in A. And so we do all that, and we could say, therefore, 2 is true. And we're done. We've rigorously proved, other than my squiggly lines that skipped a bunch of steps, we've proven that A equals B if and only if A is a subset of B and B is a subset of A. And then if we're very highbrow, we write down QED at the end, which is an abbreviation for a Latin phrase which means which is what was to be proven. And we write that down after we've proven the thing we were trying to prove, which was that 1 is true and 2 is true. All right, so we'll formalize this when we get to the actual unit on propositional logic and proofs, but just to give you a preview of it, right? So this is a useful theorem, right? Two sets are equal if and only if one is a subset of the other, and the other is a subset of the first. So there's connections between these definitions. All right, next thing we want to talk about is power sets. So suppose we're given a set S containing, I don't know, the numbers 2 and 4. We can start to list subsets of this. So somebody tell me or type me in chat a subset of S. Okay, so someone wrote 2. Let's go ahead and put it in curly brackets to separate it from just a number. So that's a good subset. All right, somebody wrote a 4. I'll go ahead and put that in curly brackets. That's another subset. All right, somebody wrote this. That's the empty set. That is a subset of S, guaranteed. And somebody else wrote 4, 2. That's also a subset. That's S itself. Remember, the order doesn't matter. So this is the same as S. Are there any other subsets?
Order doesn't matter, right?
Order does not matter, that's right.
So I don't think there's any more.
I think you're correct. There are only 4 subsets of this. Well, what if we make a set containing all of these subsets? I've got a new set. It has 4 things in it. And it's not just 4 random things. It's not a bird, a chicken, a piece of cheese, and a pen. It's 4 things that are each a subset of our original set S. And in fact, it's the collection of all possible subsets of our original set S. And that's a really useful set, and so we have a special symbol for that. And this is called the power set. So this is the power set of S, and we can write it with this script P followed by the name of the set. So the power set of S is the set containing all the subsets of S. Now suppose I have a bigger set. So the power set of T will be all the subsets of T. So what are some of the subsets of T? And yes, the power set always contains the empty set, because that's always a subset of any set. All right, we've got the set containing A. We've got B. We've got C. We got D. We got our singleton sets. We got A, B, C. ABD, good. AB. AC. We got half of them so far. I'm not going to go through all of them. I'll give you one that's a freebie though. Right, the set itself. That's always easy to put in. AD. And then there's a whole bunch of sets that have three things. So we've got ABC, ABD, we've also got BCD. And we've got more sets with two things. We got AB, AC, AD. There's also BC, BD, and CD.
Could we include the power set of ABC?
The power set of ABC would be... a set containing a bunch of other sets. And this set of sets is not going to be one of the elements in here. Every element in here is a set of letters. This is a set of sets. And that's an important difference, actually. Does that make sense?
Yes, thank you.
Okay, we'll dig into that example in a few minutes. All right, so power set of T is going to end up being 16 elements. And when we had two things, we ended up with 4 elements in our power set. And if we have 3 things, let me go ahead and show you the members of this power set. There's the power set of a set of 3 elements. 1, 2, 3, 4, 5, 6, 7, 8 things. So here's the number of elements in T. Here's the number of elements in the power set of T. So 2 things, we have 4 elements. 3 things, we have 8 elements. 4 things, we have 16 elements. What about a singleton set? Suppose S is the set just containing one element A. What are all the subsets of S?
A and the empty set.
Yeah, so the set consisting of A and the empty set. So if you have one element in T, you have 2 elements in its power set. And so somebody suggested that this looks like 2 raised to the number of elements tells you how many things are in the power set. And that is in fact a valid rule. So if you have a set with 5 elements, the power set will contain 32 elements, 2 to the 5th. All right, always play with edge cases. Edge cases are where all the good stuff happens, right? What happens if we take this to an extreme? Suppose that S is the empty set. What does the power set of the empty set look like? So yeah, empty set is being represented by a 0 with a slash through it. It kind of looks like a phi, but I think it's technically a different symbol. So yeah, so the only subset of the empty set is the empty set. So the empty set contained 0 things. Let me squeeze this in on the top here. The empty set contained 0 elements. How many elements are in the power set? 1. Because this is not the empty set. This is a set containing one thing. The thing contained in there happens to be the empty set, but this itself is not empty. It has one element. So 0 elements, we have one thing in the power set. 1 element, we have 2 things. And yeah, that sticks with the same rule. Take 2, raise it to the number of elements in T. That's the number of elements in the power set. So that is a good rule. And it's a rule we're going to come back and we're going to visit time and time again. We're going to see this in so many different forms. And you're going to encounter this in programming classes. And you're going to encounter it when you write loops. And it's going to pop up all over your life. You're going to get to know it really well. This idea of the number of subsets is equal to 2 to the number of elements in the set. That'll be a recurring theme. And we have some notation we can use. So let me talk about something called cardinality. So this is for a finite set S. Finite set means it has a finite number of things in it. So for a finite set S, we can define the cardinality of S, which we write as just S with absolute symbol bars, absolute value bars around it. This is just the number of elements in S. So if S looks like this, the cardinality of S is 2 because it has 2 things inside. So it's a fancy sounding term for describing how much stuff is in your set. But this only works for finite sets. If my set A is the set of all positive odd numbers, and I say, what's the cardinality of A? We don't have an answer for that yet. We will later. But it's not a finite set, so the cardinality is not the number of things in the set, because there is no number that represents how many things are in this set. The number 1,000,000 is too small, the number 1,000,000,000 is too small, and the symbol infinity is not a number. Infinity is not an integer. That should be a t-shirt. Infinity is not an integer. It's something different. So we can't write the cardinality of A is equal to infinity symbol. But we'll do something much more fun than that. Is there such a thing as negative elements? I don't think so. I mean, you can have negative numbers that are elements, but you can't have a set with negative cardinality. That's a cool question, though. And yeah, infinity is a concept. Very much so. So we could take this thing we just did about power sets, and we could write, for a finite set S, the cardinality of the power set of S is equal to 2 raised to the cardinality of S. And that's a valid rule. We will prove that in a few weeks. We'll prove it using something called mathematical induction, which is another one of the major takeaways from this course. And it's another thing that ties directly into programming and into proving that your algorithms work, or at least convincing yourself that your algorithms work. And one of the things we'll prove with mathematical induction is this property right here. But again, we'll visit that in a lot of different forms. Alright, so here's something quirky you can do. Power set of the empty set is a set containing one thing, which is the empty set itself. What if we take the power set of the empty set? Well, that's the power set of the empty set is this. So now we want to list all the subsets of this thing. So what are the subsets of that? And if you want to write it, you can use a 0 instead of the 0 with a slash through it. So what are some subsets of that? Right, the set itself is definitely a subset. And the empty set is a subset. And that's it. Those are the two subsets of this thing right here. So I can ask for the power set of the power set of the power set of the empty set. And that's the power set of this set, which is a set containing the empty set and the empty set itself. And now we can list all the subsets of this thing. And I won't make you type them out, but what are the possible subsets here? Well, there's the singleton set containing just this element here. There's a singleton set containing just this first element. There's the original set itself. And there's the empty set. So the empty set had 0 elements in it. The power set had 1. The power set of that had 2. The power set of that has 4, and so on. You can build up a whole system of arithmetic just by taking power sets of the empty set. And we're literally starting with nothing, right? The empty set is almost nothing. It's not, it's a set. But it contains nothing. But we can get to something very much not nothing by using the power set. So that's something to play with. All right, let's revisit Cartesian products. So we talked about these a little in the very beginning. Let's revisit them. So remember, Cartesian product of two sets is the set of all ordered pairs. Okay, so ordered pairs is a set of collection of two things where the order matters. So for example, we would write parentheses A comma B. This is the first thing, this is the second thing. Okay, it's an ordered pair, so this is different from this ordered pair. Unless A and B happen to be the same thing. So like 2 comma 2 would be the same as 2 comma 2. But if A and B are different, this ordered pair is different from that ordered pair. Okay, that's fundamentally different from set theory, where, for example, the set AB is exactly the same as the set BA. Okay, these are different. And so given two sets A and B, the cross product, remember, is a collection of ordered pairs where A comes from the first set and B comes from the second set. And so we have an interesting consequence, which is that in general, A cross B is not the same as B cross A. How could it be? Because this is a collection of ordered pairs where the first element comes from A, and this will be a collection of ordered pairs where the first element comes from B. Well, A might be a set of numbers and B might be a set of farm animals. And so this will be number comma animal, number comma animal. This will be animal comma number, animal comma number. right? They're not going to be equal. And if the elements aren't the same in these two sets, the sets aren't equal. So the Cartesian product is not what we would call commutative. So commutative means, you know, A plus B equals B plus A. A times B equals B times A. But for cross products, Cartesian product, A cross B is not generally the same as B cross A. And things get really interesting when you have non-commutivity. And yeah, you could very well be flashing back to linear algebra now. So what's another example, especially if you've had linear algebra, where you find this property that A operated with B is not the same as B operated with A? And I'm guessing this is why you're flashing back, or one reason. So how about matrix multiplication? So we do some matrix multiplication in 120 sometimes when we talk about solving KVL, KCL. Math 215, linear algebra, you do a lot of matrix multiplication. And one of the things you learn pretty early on is that multiplying matrix A by B is generally not the same as multiplying B by A. In fact, in some cases, this might be a totally valid thing to do, and this might not even be defined. Right? If the dimensions of your matrices don't line up right, you can't necessarily multiply them. So matrix multiplication is very definitely non-commutative also. We'll talk about matrices on Friday. Let's see. Question, could some components be expressions? Components of a set, you mean? Yes, definitely. If you mean something else, chat me what you had in mind. Oh yeah, so in matrices you can definitely have expressions in there too. All right, and we can do this with more than two things. We could take A cross B cross C, and that would be a set of what we can call ordered three tuples. It's hard to say ordered three tuple and look serious when you do it. Ordered three tuples. But this is the set of all things A, B, C, where A comes from the first set, B comes from the second set, and C comes from the third set. And so the same idea, right? You just pull something out from each of those sets, but the order is significant. Okay, and so here's an interesting question someone just asked. Is A cross B cross C different from A cross B in parentheses cross C? Technically, yes. Technically, this is, you know, a set of three tuples, whereas this is going to be a set of ordered pairs crossed with a set C. You're going to get a new set of ordered pairs where the first thing in the ordered pair is a tuple, and the second thing comes from C. But I've seen this used to represent that, and vice versa. And usually when we take a cross product of multiple sets, I think more often than not we're heading for something like this. If you have 5 sets, we want a 5 tuple. But technically, if you cross A with B first, you're going to get something like this, and then when you cross those with C, you get something very different. So yeah, that's a good question. And hopefully it's not something that trips us up down the road. All right, cool. So yeah, I like that people are thinking about these things. All right, let me show you a particular case where this tuple business will actually be familiar. let A equal, let's make it the closed interval 0, comma 1, which is the set of all, and I'm going to go to real numbers here for a few minutes, the set of all real numbers such that that number is bigger than or equal to 0 and less than or equal to 1. And let B be the real interval, let's say 2, comma 3. So the set of all real numbers bigger than or equal to and less than or equal to 3. So if I draw a good old number line, this is my interval A, this is my interval B. If I take the Cartesian product, I'm going to get a set of ordered pairs, where the first element comes from A and the second element comes from B. So for example, I could have the number 0.5, comma 2.5, right? Because 0.5 is in A and 2.5 is in B. I could have the number 0.3 and 2.8. I could have the number 0.9 and 2.2. There's a lot of ordered pairs I can pick from. Because there's an infinite number of things in A and an infinite number of things in B, I'm going to have an infinite number of ordered pairs. But there's an easy way to represent those on a real number plane. I can represent each of these ordered pairs as a point in this plane, where the first number is how far I go over in X, the second number is how far I go up in Y. And it turns out the cross product of these two intervals is going to look exactly like this. It's going to be everything in this rectangular region. Because every point in here has an X value between 0 and 1, and a Y value between 2 and 3. Which means the X value comes from set A, the Y value comes from set B. So here's a beautiful geometric interpretation of Cartesian products. The Cartesian product of two intervals will simply be a rectangular region in two-dimensional space where its placement in X is based on the first interval, its placement on Y is based on the second interval. And so we get this nice filled-in region all the way up to and including the borders. And it includes the borders because, for example, the number 1 is an element of A, and 2 is an element of B, so the tuple 1, comma 2 is in that Cartesian product. Well, 1, comma 2, that's this corner right here. And 1, comma 3, and 0, comma 2, and 0, comma 3, and everything along each of these edges is included in that Cartesian product. Cartesian as in Descartes, right, who, studied this. Cartesian coordinates, Cartesian number system. That's all the same stuff. All right, and just to round it out, suppose A is what we called an open interval, so the set of all real numbers, which are strictly bigger than 0 and strictly less than 1. And B is our open interval from 2 to 3. Well, now if we want to draw the cross product, what we're going to end up with is what we call an open region. It's going to include everything in here, but not the boundary of that rectangle. Right? It doesn't include anything on this lower edge because this is a line where y is equal to 2, and 2 is not an element of B. Right? B contains all the real numbers that are bigger than 2, but not 2 itself. So open intervals, Cartesian product gives us an open region. All right, so did I place it in the wrong spot? I did place it in the wrong spot. There we go. I just made it worse. There we go. Change the problem. All right, yeah, so from 0 to 1 in x and from 2 to 3 in y. Thank you for the correction. All right, so that's Cartesian products, okay? And again, you can spend a semester or 2 at a university program if you're studying math, taking a point set topology course or a real analysis course, and just study these open and closed intervals and develop all kinds of things from it. Yeah, that was a nice hack on my diagram, thanks. All right, so let's see. I checked in class, officially ends at, oh, I forgot, I think it's 1:55. So we'll end there. All right, let's talk about set operations. So one thing we like to do with this stuff is we like to make new stuff from old stuff. Okay, this is a recurring theme. We do it in programming, we do it in logic, and we do it in math. So making new things from old things. So we're going to talk about set operations. All right, so given 2 sets A and B, we can define the union of sets So the union of A and B equals the set of all elements E such that E is in A or E is in B. We can define the intersection of A and B, and that's the set of all elements such that the element is in A and the element is also in B. We can write the complement of a set and that means the set of all elements which are not in A. So it's everything left after you take off what's in A. And we got to be a little careful here when we talk about complements to know what the universe consists of. So let me do some examples, and let's see how we get into trouble with complements. So let A be the set 1, 2, 3, 4. Let B be the set 2, 4, 6, 8. So A union B is the set of all things that are in A or in B. So that would be 1, 2, 3, 4, 6, and 8. I don't want to list the number 2 twice. That gets a frowny face on the homework, right? 2 is an element of the set, so I list 2 inside the curly brackets. Listing 2 twice is kind of a meaningless redundancy. So the union would consist of 1, 2, 3, 4, 6, and 8. The intersection is a set of all things that are in A and also in B. Well, so the intersection has to be things in A. Could it be 1? No, because that's not in B. but it could be 2 because that's in B. 3 is not in B. Could it be 4? Yes, 4 is also in B. And those are the only things in the intersection. All right, the complement can be tricky. The complement is all the things that are not in A. So what's not in A? Well, for example, 6 and 8 are not in A. But is there anything else that's missing from our set A? It doesn't have a 0 in it. It doesn't have a 5 in it. It doesn't have a smiley face in it. It doesn't have a scribble in it. It doesn't have a pen in it. There's a whole lot of things that are not in my set A, right? So the complement is not always well defined unless you know what the universe of possible things is. So when you define the complement of a set, you've got to know what the universe is. For example, if I say working over the universe of positive integers, well then I could say the complement of A is 5, 6, 7, 8, ... If I'm working over real numbers, there's a whole lot of things that are not in A. It doesn't have pi, it doesn't have the square root of 2, it doesn't have 1.5, it doesn't have 3.3, it doesn't have any of these things, it doesn't have negative anything, right? If I'm working over the universe of all things, which is not something we want to do, then it's also missing the smiley face and the squiggle and the pen and so on. So a lot of times when we talk about complement, we talk about the complement inside another set. And so we'll use this notation A subtract B, or sometimes you see it written with a plain old subtraction. This is A minus B, or we could say A take away B. But the proper, most formal way to describe this is the complement of A in B. And it's equal to the set of all elements in A such that, set of all elements in B which are not contained in A. So our kind of uncontrolled complement was just a set of things not in A. But when we take the complement in another set, we say the set of things in that universe, right, B, that are not contained in A. And this is really the way to define a complement. And then the shorthand notation A bar is really the complement of your set in the universe of all possible things. So in the universal set. I think I'm writing this backwards. Rewind the past few minutes. Sorry. All right. So A take away B, A minus B, the complement of B in A is a set of all things in the universe, all things in the universe that are not in B. Okay, it's basically start with the universe, throw away everything that's in B. So the plain old complement, when we just write a set with a bar on top, that's really the set of everything in the universe that's not in A. Okay, so take the universe, throw away everything that's in A. So let's do some examples and make this solid. Suppose A is a set 2, 4, 6, and B is a set of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So A take away B says start with the set A, throw away everything that's in B. So this is a set of all elements in A which are not in B. Well, is there any element in A that's not in B? Right? The element 2 is in B, the element 4 is in B, the element 6 is in B. So this is actually the empty set. We're starting with this set, we're throwing away everything that's in B. Right? So subtraction is sort of the most intuitive way to write complements. Start with this, subtract off B. If we do this in the other direction, start off with a set B, throw away everything that's in A, we just get that. So start with everything in B, throw away everything in A. If this is our entire universe, if our whole life is only 10 integers, 1 through 10, we can just write the complement of A, and it's, you know, everything that's not in A, where everything means everything in our universe, everything in B. And you'll also see the notation sometimes in print, A with a little c on top. That means the complement of the set.
B minus A would have 10 in it, right?
Correct. Thank you. All right, and if we go back to our Venn diagram, right, this was a set of cookies. The complement of the set of cookies would be everything that's not in here, right? But it's everything that's in the universe but not in here. And this shaded area here was the complement of the union of the set of cookies and the set of foods with chocolate. And this backwards shaded area in here is the intersection of this set with that set. All right, well, once we have some definitions, we can start putting them together. So we can talk about properties of set operations. So set identities. So we can start writing down facts. For example, A union itself is just equal to A. A intersected with itself is just equal to A. A union with the empty set is a set of everything that's in A or in the empty set. Well, there's nothing in the empty set, right? So this is just going to be A. A intersected with the empty set is everything that's in A and also in the empty set. Well, there is nothing in the empty set. So any element we think of, it might be in A, it's not going to be in the empty set, so it can't be in both. So there can't be any elements in here. This intersection is empty. If we take A and we union the universe, that's a weird looking universe, the universal set, everything that's in A or in the universe, that's just the universe. If we take A and we intersect with the universal set, this is everything that's in A and also a member of the universe, that's just going to be A. If we take the complement of A, we just get back A, where this means the complement of A in the universal set. So we have these identities. We also have, if we take B and C, take their union, and then union with A, it's the same as taking A and B's union and then unioning with C. And the same thing with intersections. This is called associativity. The order in which we take unions or intersections doesn't matter. A union B is the same as B union A. A intersect B is the same as B intersect A. That's called commutativity. And yeah, this was a double negation, so the complement of A. So like this. And that's the same as A. If we take A and we take its union with the complement, what do you think we get? Right? We get the universe set, correct. Because this is everything that's in A or everything that's not in A. Well, that's the universal set. What about the intersection of A with its complement? Right? We get the null set or the empty set. Because this means, give me the set of everything that's in A and also not in A. And for most sets, we can't find an element that's both in the set and not in the set. So there's nothing in this intersection, so that's the empty set. Is anybody flashing back to some past course where you might have seen something that feels similar to this? Linear algebra, that's one of them. Digital logic, engineering 250. These are the identities of Boolean algebra. In Boolean algebra, we say things like A or A is equal to A or false is equal to A and false is equal to false, A or true is equal to true, A and true is equal to A, right? Or maybe we use ones and zeros instead of true and false, right? But these are things that we encounter in Engineering 250 when we do Boolean logic. And commutativity and associativity come out of there also. And also distribution. We can take A and union it with B intersect C, and that's A union B intersected with A union C. And we also get everybody's favorite. Anybody know what that's called?
Is that De Morgan's?
That's De Morgan's theorem. De Morgan's going to be a good friend this quarter. And there's an analog to this which says the complement of the intersection is the union of the complements. That's another version of De Morgan's theorem. And it works for sets just as well as it works for Boolean operators. Someone said there was an alternative to interval notation that used the union symbol back in college algebra. I believe you're right, and I don't know if I can pull it out of my head right now. But we'll talk about unions on Friday, and maybe it'll pop up then. Alright, so all the stuff that we learned in 250 when we did Boolean stuff is going to apply to sets, right? And if you do sets first, you can get to Boolean stuff. Boolean algebra came after set theory, I believe. Maybe not. But they're duals to each other. Alright, so this brings us to how do we prove things? Suppose we want to prove that A is equal to A union B intersect A. So let's suppose A equals 1, 3, 5, and B equals 3, 5, 7. While B intersect A is just the things in common, that's 3, 5. And A union B intersect A is 1, 3, 5 union with 3, 5. That's just going to be 1, 3, 5, which is in fact equal to set A. And we'd like to know, is this always true? Or did we just happen to pick lucky sets? So we can use something called membership tables. And here's the idea. And we'll dig into this more on Friday, but here's the idea. Suppose I have a set A and I have a set B. And I think of any object in the universe. Okay? Suppose I'm working over the set of numbers. For any object I pick in the universe, there's exactly one of 4 possibilities. It could be that the element I thought of is not a member of A and it's not a member of B. Or it could be a member of A but not B. Or it could be a member of B but not A. Or it could be a member of both A and B. Those are the only 4 possibilities. So I'm going to enumerate those in a table, which we call a membership table. And I'm going to use ones and zeros. If my element is not a member of A, I'm going to write a 0. And if it's not a member of B, I'm going to write a 0. And I'm going to find there's 4 possibilities for anything I think of in the universe. It's in neither A and B, it's in B but not A, it's in A but not B, or it's in A and B both. And now I can write down, for example, what it means to take the intersection of B and A. So I've picked some element from the universe. I'm holding it in my brain. Maybe it's an elephant, maybe it's the number 11. If the number I'm thinking of, if the thing I'm thinking of is not in A or it's not in B, can it possibly be in the intersection? Absolutely not. And if it's in B but not in A, it's also not in the intersection. And if it's in A but it's not in B, it's not in the intersection. But if it's in both A and B, it is in the intersection. So there's a membership table for the intersection operation. And just for completeness, if I wanted to write the union, well, if the thing I'm thinking of is not in A or B, it can't be in the union. But if it's in B, it will be in the union. If it's in A, it'll be in the union. And if it's in both, it'll also be in the union. So yes, intersections are like ands, and unions are like ors. This is a map from set theory to Boolean logic. And you know, if I wanted to write the complement, well, if my element is not in A, it's in the complement. And if my element is in A, it's not in the complement. Right? This is just a plain old truth table. So let's finish our proof. Let's write a column for A union B intersect A. And so what I'm going to do is I'm going to take this column, and I'm going to take this column, and I'm going to write down the ones and zeros for a union. So if I thought of an element and it turns out it's not in A and it's not in the intersection, then it's not in their union. Here I thought of an element, it's not in A, it's not in the intersection, it's not in the union. But here's something which is in A, so it's in the union, and here it's in both A and B, so it's in the union also. And now, based on that, what can I do? I can say, hey, look at this column. Exactly the same as this column. What's the punchline here? For any element in the universe, that element belongs to the set A if and only if it also belongs to this set. If it's in A, it's in this set. If it's not in A, it's not in this set. If it's not in this set, it's not in A. If it's in this set, it's in A. That was our definition of equality from Monday. Two sets were equal if belonging to one set meant that you necessarily belong to the other and vice versa. So based on this membership table, we can now write an equality. And bang, there's our proof. So in 250 it's called a truth table because it's used to show the truth of some statement. Same thing with a membership table. We can use this and we can say definitively, okay, this is exactly the same thing as that. All right, so lots of parallels, right? We'll see these popping up throughout the quarter, and we'll come back to them frequently, but that's one of the parallels. All right, so I want to talk about unions and intersections of collections of sets on Friday. We'll talk a little bit about functions, and then we'll dig into cardinality. We'll have some fun. We'll play with some paradoxes. We'll talk about infinities and things like that. And that will pretty much round out our discussion of set theory. And then we'll be able to move on to some other things next week. All right, that's all I got for today. Thank you very much. Have a good one.